In this segment, we're going to look at the problem of testing if a graph is a biclique. And particularly, we're going to assume a dense graph model in which the queries will be of the form, is there an edge between these two pair of vertices? And in particular, this is an excellent example where the test and the enforce and test technique is exercised. So without further ado, let's look at this problem. Well, we need to test whether the graph is a biclique. And so what is a biclique? Well, the vertex set V should be we should be able to partition it into subsets V1 and V2 such that of course they don't intersect, and the union of V1 and V2 is the entire vertex set. And moreover, it's a biclique if the edge set is exactly equal to V1 cross V2. So every pair of vertices such that one of them is in V1 and the other one is in V2 must have an edge between them. And that's what a biclique is. And of course, we are interested in testing whether the given graph is a biclique. Okay? And of course, we have to assume that there is a promise. And what is a promise here? We're guaranteed that the graph is either a biclique, which means there exists such a partition V1 and V2 with edges, all possible edges going across V1 and V2, or the graph is epsilon far from being a biclique. Okay. What does that even mean? Well, let's look at it shortly. But as we mentioned earlier, we need to answer this question just by asking queries of a very specific nature. This is the dense graph model, and so we cannot assume that the graph is stored in, we typically don't assume that the graph is stored in sort of an adjacency list type of format. It's more like a giant matrix, and so we can ask the question, is there an edge between vertex U and vertex V? And using queries of that type, we should be able to answer this question of whether the graph is a biclique. So what does it mean for a graph to be far from being a biclique, in particular epsilon far from being a biclique? First of all, what does it mean for a graph to not be a biclique? Well, any way in which you partition it, the edge set should not be equal to V1 cross V2. That's what it means for a graph to not be a biclique. But for it to be far from being a biclique, for all partitions V1 and V2, the number of edges that need to be added or deleted to make V1 and V2 a biclique partition should be at least epsilon n squared. And if so, sometimes we may need to add a few edges because these could be edges in V1 cross V2 that are missing, or some spurious edges that are lying between two vertices in V1 or lying between two vertices in V2 need to be deleted. And we need to make epsilon n squared such modifications before we arrive at a partition V1 and V2 such that this partition leads to a biclique partition. Okay. Another way of succinctly saying the same thing is that the cardinality of the following symmetric difference, in other words, in particular, E minus V1 cross V2, these are the edges that are in E that shouldn't be in the biclique partition. Union V1 cross V2 minus E. These are the edges that should be there but are missing. The union of these two differences is called a symmetric difference between the set E, which actually exists in the graph, and the set V1 cross V2, which should be the edge set for the biclique, that symmetric difference has to have a cardinality at least epsilon n squared. So this is what it means for a graph to be epsilon far from being a biclique. Okay, so let's remind ourselves, we have a graph, we know that it's either a biclique or it's epsilon far from being a biclique. And we need to test and find out whether which category it belongs to. Okay, and we want to arrive at an algorithm that exercises this enforce and test technique. So here's how the algorithm works. There's the enforce part, and then there's going to be the test part. And believe it or not, the enforce part for this algorithm is simply just one step. Pick a vertex v0 arbitrarily. It could be any vertex. And you may say, well, is that it? And as it turns out, yes, but look at the power of this one single step. As soon as we pick this vertex v0, this immediately enforces a structure. Now, if the graph is in fact a biclique, let's, without loss of generality, assume v0 is in v1. All the neighbors of v0 will have to be in v2. And all the non-neighbors of v1 must be in v0 must be in the set v1. And so the entire structure of the graph is enforced, and this makes it easy for us to test whether there is a violation of this enforced structure. So if the graph is in fact a biclique, this is the way the structure has to exist. All neighbors of v0 must be in the set v2, and all non-neighbors of v0 must be in the set v1. So let's go ahead and test if this is in fact holding true. So how do we do that? Here's how we do it. This part is again very simple. We simply sample some theta of 1 over epsilon number of pairs of vertices. So we simply run a for loop from i equal to 1 to 2 over epsilon, and each iteration of the for loop comprises picking a pair of vertices ui, vi, and these are chosen uniformly at random. And now we test if the biclique property is violated. If it is violated, we immediately reject the instance. But if it's not violated, we continue on. And after testing 2 over epsilon of these pairs, if we still haven't found any such violating pair, then we terminate the algorithm and accept the instance as one that is indeed a biclique. And of course, now we need to ask ourselves, what does it even mean to be able to detect a violation? Well, let's look at this a bit carefully. Recall that we have picked a vertex v0, and that meant that neighbors of v0 went into v2 and non-neighbors of v0 went into v1. What are the ways in which we can encounter violating pairs? Well, we can have edges of the form shown here, where both ui and vi, the sampled pair, both are non-neighbors of v0. Or you can have ui, which is a non-neighbor, and vi, which is a neighbor, but this means that there must be an edge between the two of them. And if that edge is missing, then that's another violation. And here's a third type of violation. ui and vi are both neighbors of v0 and therefore are in v2, but they end up having at the edge an edge between them. And that edge also shouldn't exist. And so there are these three types of violations that you can encounter. The first and the last type of violation that we saw are extra edges that need to be deleted in order to make this the structure actually a biclique. And the second Second one is a missing edge. So this edge must be added in order to convert this into a biclique. And remember that there are epsilon n such modifications. If the graph is indeed not a biclique, there are epsilon n such modifications that are needed before the graph can become a biclique. Okay, so that that means that our samples. I mean, this gives us the possibility of, or rather, the good probability of capturing such violation. Okay, let's analyze this a bit carefully. Well, if G is in fact a biclique, then we're always going to be correct because we're never going to find a violation. So the algorithm is going to output an accept verdict, which is going to be always correct. So it boils down to being able to reject a graph that is epsilon far from being a biclique. So for rest of the analysis, we're going to assume that our graph is epsilon far from being a biclique, which means, remember, that the number of violating pairs is at least is greater than epsilon n squared. And so now let's see what happens. We need to ensure that the probability with which we reject such a graph is at least a half. Okay, so let's see how this can work out. What is the probability? Let's focus on one iteration I. What is the probability that the pair chosen in that iteration I is a violating pair? Well, there are total of, n choose 2 pairs that we can choose from. Let's even approximate that to n squared pairs, out of which at least epsilon n squared pairs are violating pairs. So if you choose pairs uniformly at random, then there's a probability epsilon that at least a probability epsilon that we will be choosing a violating pair. Okay, but what could happen is we may end up never choosing a violating pair. But what's the probability of that happening? Well, for one iteration, it's going to be 1 minus epsilon at most, and over 2 over epsilon iterations, the probability is going to be 1 minus epsilon, the whole raised to 2 over epsilon, which is going to be at most epsilon to the minus 2 when you apply the formula that 1 minus x is at most e to the minus x. And so now we can ask, what is the probability that we will be correct? This step is talking about the probability that we will be incorrect, that we will not be able to pick any violating pair. Well, that's just the probability that the algorithm will actually reject graph is simply the probability that some violating pair will be chosen, which is simply at least 1 minus epsilon e to the minus 2. And since e to the minus 2 is small, it's like a less than a third, we ensure that that the probabilities of correctly rejecting the algorithm G is at least 2/3. So you can see that this enforce and test technique makes the analysis very clean and simple. The first step enforces a certain structure, and then it becomes easy to test against that enforced structure. So that's the main idea behind this approach. And then once that, when we are, the trick is to design an enforcement that will help us to test and reject instances that are far from having the property. That's the key insight. So now this brings us to the end of this second segment. In the next subsequent segment, we will look at testing whether a given graph is bipartite or not, again in the dense graph model. And that's a bit more of a realistic problem, and one step more interesting and challenging in terms of the algorithm and the analysis. So that's going to be the next segment.